let's take a look at these. So first off, actually, we'll just go down the line again with this one and have people give me stuff. So step one, Issa, step one.
H0 is rho equals 0.
Mm-hmm.
And then H1 is rho is not equal to 0.
Great. Step two, Una.
Alpha equals 0.05.
0.05. Was the alpha given?
No.
Yes.
Okay. If the alpha is not given, the alpha should be assumed to be 0.05. Everybody good? Okay, Shauna, step three.
Line reg t-test L1, L2, 1 not equal to, and P equals 0.3176.
PB equals, what was it?
0.3176. R equals 0.4446. And then do you want A and B
Yep.
and T? Okay, so A is 63.87. B is 0.4427.
Great. All right, next step. Four. Devin, have I called on you yet?
Yeah.
Isaiah, go ahead.
Number 4.
I'm sorry?
Number 4, you said?
Yeah, step four.
0.3176, or the
Mm-hmm.
point value.
Yep.
Is greater than?
Mm-hmm.
And 0.05.
Great. So then, what's our decision?
Not reject.
Not reject H naught. Which means, is it a line or not a line? With your neighbors, everyone take 10 seconds with your neighbors. Is it a line or not a line?
Thank you.
The way I think it is,
It's close to
Yeah.
0.
If we do not reject H naught, then it is not a line. Right? Because H naught says that we are right smack dab in the middle. Right? Chaos. Right? That's what H naught says. And if we don't reject it, then that means that we're close to chaos. Right? It's not a line. Great. All right. And so then step 5. Sophia, did I call you yet?
Yeah, but I can.
That's okay. Michael, have I called you yet?
No.
Great.
So there's not enough evidence to say that there's correlation between size and revenue.
Great. Not enough evidence. I just put of correlation. We can do that, like to say or of between. What is this?
Size and
Casino
revenue.
size and revenue. Great. All right, so then comes the next part. We need to predict. Predict revenue for 190 square feet. Okay, so is that 190 square feet, is that my X or my Y?
Y.
190 square feet?
X. Your X.
That's my X. So this is my X for X equals 190. Does that make sense? So I need to figure out what the Y is. Revenue is my Y when X is 190. All right, so let's see. Well, I have my linear regression line. Y equals 63.87 plus 0.4427. I can just pop in 190 there. Yeah?
No.
No, why not?
Because it's not a line.
It's not a line. From here, I did not reject H naught. It is not a line. So I cannot use this line to predict it. That makes no sense. Right, if your data is not in a line, don't use a line to predict. Instead, we should use what?
2-bar stack.
Yep. So we're going to do 2-bar stats of L1, L2, I think it's 1. You might have put a 1 in if you,
I thought we don't put.
Oh, you leave it blank? Yeah. And if you're not sure how to do that, this is how you do that. I'll show you real quick. So I don't have the same data as you have in there, but you would do stat calc 2-bar stats of, here, I'll make it clearer. Stat calc 2-bar stats. And I'm just going to put second 1 to get L1 in there, comma, which is above the 7, second 2. And that will give me my X bar. If I arrow down a little bit, it'll give me my Y bar. Mine's going to be different than yours because I don't have the same data in mine as you have. But that's how you find it. So we end up getting a Y bar of, what'd you get for your Y bar? 1.4,
134.7.
oh, 134.7?
Yeah.
And then what was your X bar? Did you animate it the X bar? 160?
Yeah.
Okay.
Okay.
So our best guess at revenue is 134.7 billion dollars, whatever it is. Our best guess at casino size is 160 square feet. Is that, or must be 1,000 square feet. Those are our best predictors. What are we trying to find? We're trying to predict X or Y. Y, revenue. So our best guess is,
So do you only do y equals a plus bx when it's a line?
yes.
Right, okay.
Yep. Because why would you use a line to predict if your data is not a line?
No, yeah, that makes sense.
So Y equals Y bar,
First time?
134.7 million. Don't forget to label it, $1,000,000. Everybody all on board? There. So you will get this on the final when you see this problem. And one similar to it. Make sure that you practice, do the homework and practice it. The final is still 2 weeks away from Thursday, so it's still a little bit away. So don't forget it between now and 2 weeks from Thursday. Okay. All right. Now, ASCOM's quartet. So what we should do is we should also always graph our data, because here's the thing. I want to take a look up here real quick. All 4 of these data sets have the exact same R and the exact same linear regression line. So their A and B are the same, and their R is the same. So you cannot just rely upon R, because that first one, would you say that that line matches up pretty well with the data? Yeah, the first one does. The second one, no. My data, that's a parabola, that's a curve. Does everyone kind of see that one?
Yeah.
This one here, the line should be more like, so this one's okay. The first one. This one's okay. This one, it should be more like that. Does everyone sort of see that? This one, the line should be more like that. And this one, the line should be more like that. Does everyone sort of agree?
Yeah.
What's going on is we have these little, well, this is a curve, so that's kind of messed up. These are what we call outliers over here. So, and they're kind of messing things up. So someone found and created these data points, and they found it, they moved them around, so they matched up perfectly, so they all had the exact same R, and then the exact same linear regression line, just to prove to you the fact that you really need to graph your data in theory to confirm that it looks like what you think it does and it isn't one of these other things. So on your homework, it will ask you at some point to find the R for your data, and then, there'll be one like these two, and then it'll ask you to remove the outlier. I had a student ask me and say, what do you mean remove the outlier? You have to graph it, and then you'll see that one one does not belong. Can everyone see how these two are the ones that don't belong? So you'll need to know how to graph it. This is how you graph it. Go to your, you've got your data in here, stat, edit. I have your data in your list one and list two. You need to go to second, does anyone see here where it says stat plot in this corner right here? It's in blue, so you have to use second first. So second stat plot. And your number one will probably be off. It'll probably be over here where it's off. So it'll see it says plot one off. So hit on number one, hit enter, and just click on the on, and hit enter on the on, and now it's on the on. For this one, you probably want the first one, the dotted lines. Your X's should be L1, your Y should be L2. That should hopefully be in there already. And then you can use anything you want for the marks. The mark doesn't matter, it can be any one of those. Once you have this, so you should probably write down second stat plot, that might help you. And then you want to hit zoom 9. So I'm going to write down zoom 9, you're going to need that also. Zoom is the smack dab middle of the button in the middle top up here. If I hit zoom 9, it'll graph it for me. And then I can see, oh look, those ones all belong, that one doesn't. And you should be able to get a sense of where it is so that you should know, and from looking at your data, you also should be able to kind of tell that there's one that's totally crazy, different than the rest.
Well, you can move your arrows to the dot and it will tell you X.
Oh, nice. Okay. On the homework? Or on the,
on the end here.
oh, really?
Yeah.
How cool is that? So if I arrow
Up or
Up?
just, yeah. See the little, and then just go to the outlier, the one on top that you think is
oh,
the
that's what you're
outlier,
saying. So I can go, I would say,
to that dot.
yep, I can just move that little arrow, the little X
Yeah.
up.
Cool.
And then, yeah, that's kind of nifty. Thank you for that.
And then go.
So I know it's kind of right around,
Yeah.
oh, it gives you a little circle when I'm on it.
Yep.
It
And then
blinks
you
at
do
me.
your X and Y.
And then it tells me what the X and Y is. Okay, very good. All right, all good? Okay, so it's off a tiny bit, but yeah.
Somewhere.
Okay, good deal. So that is how you do that homework problem. Oh, that was actually what I meant to do to tell you with this one, right? So I did have it. So again, you're going to want to do X in L1. L2, you're going to put in your Y's, and then you're going to do second stat plot. And then you're going to turn plot 1 on. And then you're going to do zoom 9. And that will give you, that'll get you the graph. Okay. All right, so now we're going to jump into chapter 11. These are the things we're covering in chapter 11. You're going to test the distribution for goodness of fit. And then we're going to also test two variables for independence and homogeneity using chi-squareds. This is all, the next two sections are going to be all about chi-squareds. All right. Test for goodness of fit, the chi-squared. So this is not chi. Everyone look up, C-H-I. This is chi. Like, go fly a kite. It is a swooshy line like this. Everyone look up for a second. Swooshy line like that, and then a line like this. That's a chi. So if anyone rushes a Greek system, chi omega, that's chi, it looks like an x. It's chi squared. That is not x squared, right? This is x squared. Squared. This is chi squared. Can everyone everyone sort of see the difference between my chi-squared and my x-squared? They're not the same. The chi-squared is this swishy thing, and then the line. Right? So it's a little bit different. And again, it's pronounced chi, like kite. And so so another thing to comment on is you don't take chi and then square it. The distribution is called chi-squared. That's its name. I don't know where it came from, and I don't really want to spend time researching and talking about it, but just accept the fact that that's its name. All right, good deal. All right, so here, let's get a reader for everything starting with, well, from the beginning. Sure, why not? Issa, go ahead.
The chi-square statistic can be used to see whether a frequency distribution fits a specific pattern. This is referred to as the chi-square fitness of fit test, which tests the claim that an observed frequency distribution fits some expected frequency distribution.
Exactly. So we're going to have an expected frequency and an observed frequency, and we're going to test that they're equal to each other. So H naught, I am going to let you get away with just putting it down to symbols. The observed values, so O sub I means O sub 1, O sub 2, O sub 3, O sub 4 equals E sub 1, E sub 2 equals, so we just call that O sub I, since I goes, it has many possible values. Does that sort of make sense for folks? So the observed values equal the expected values. O sub I equals E sub I. H1 would be that what you observe is not what you expected. Your observed values do not equal your expected values. O sub I does not equal E sub I. O sub I. Sub I is the subscript the labels have. So sub I means all of your O's. O sub 1 doesn't equal E sub 1. O sub 2 doesn't equal E sub 2. You'll see it in a minute what we're talking about. It'll make more sense. Let me go ahead and pause the recording and start it again. Okay. There are some assumptions. Again, your data should be from a random sample. If you did not sample randomly, you're going to get garbage. It's going to be biased. 2, your expected frequency for each category, what you expect to get, not what you actually got, but what you expected to get, you have to have at least 5 in each category. Please note, data is categorical, not numerical. So if you're doing things like favorite color, you have to have at least 5 expected in each color, of each color. Or birth month, right? These are categories. Let's get a reader. Erin, have you read it? Great, go ahead.
O represents the observed frequency of an outcome found by tabulating the sample data. E represents the expected frequency of an outcome found by assuming that the distribution is as claimed. K represents the number of different categories or outcomes. N represents the total number of trials or observed sample values.
Right, so K and N are different. K is how many possible answers are there. If it's binomial, K would be 2. Is or isn't. Blue eyes or not blue eyes. But we're not talking about binomial anymore. Now we're talking about, because if it was binomial, we just do a proportion. Chapter 8. Now we're looking at multiple options, like blue eyes, hazel eyes, brown eyes, black eyes, right, or something like that. Multiple options. Does everyone kind of see what's going on? Mm-hmm. So now we have many different categories. And N is how many people you asked total. Good? Okay. Here is the formula for the test. Again, this is not x squared. That's chi-squared. It's just the name of it. Right? Just like rho or sigma, sorry, not sigma, rho or mu or something like that. It's just called chi-squared. That's the name of it. Don't find x and square it. Don't find chi and square it. It's just That's the name, chi-squared. It's equal to taking every observed value, subtracting what you expected to get, squaring that amount, and dividing by what you expected to get. Your degrees of freedom is how many categories you have minus 1. So degrees of freedom looks like this. It's the number of options you have minus the number of variables you have. So we only have one variable, so it's going to be categories minus 1. And so let me give you an example. But I promise you, once this chi-square makes sense today, put a little effort into it to make sure you're ready for it, and then Wednesday will be a breeze. All right, so let's take a look at what I mean. We'll do an example. The example will make a lot more sense. Quentin, go ahead and read.
A market analyst wished to see whether consumers have any preference among 5 flavors of new fruit soda. A sample of 100 people provided the following data. Is there enough evidence to reject the claim that there is no preference in the selection of fruit soda flavors? Using the data shown previously, let alpha equal 0.05. What is the expected value?
Great, thank you. So they sample 100 people. My n is 100. Everybody got that? What's my k, my number of categories? 5. Yep, there's 5 choices. Is everyone on board? Okay, so our k is 5, our n is 100, and my question to you is, what are my expected values? So I expect them to be preferred equally. I expect there to be no preference in fruit flavor sodas. If I expect them to be no difference between them, I expect them to be what?
Equal.
Equal to each other. Does that make sense? So these should all be equal to each other. If I sample 100 people, and I expect all the categories to have the same number of people in them, how many of them should there be in each category? Why don't you take 30 seconds with your neighbors and work on that. Okay, so your answer was, you expect there to be 20. How do we get that? There's 5 categories. There's 100 people, right? So they're all the same. We take n over k. 100, divide them equally amongst the 5, and we get 20 in each one. Is that, everyone kind of follow that? Okay. All right, so that's the first thing. Figure out what your expected values are. I always give you, you're always given what was observed because that's your actual data, right? We actually found 32 people like cherry, 28 like strawberry, only 16 like orange, which I think is total BS. Lime 14, and actually grape is even more BS because that's actually might be my favorite. Only 10 people? Come on, really? Grape rules. Okay. Now, the hypothesis is that there is, so you're always given the expecteds, the observeds. You always have to calculate the expecteds. The expecteds are always going to be you having to do some math to find the expecteds. And they are not always whole numbers. Okay, we'll talk about that in a minute. They can be decimals as well. All right. So state the hypothesis, identify the claim. So the first one is H naught, again, is always my no's, right? No difference. Usually it's been no difference. No correlation. In this case, it's no preference. In other words, no difference in the flavors in this case, right? No difference between the observed and the expecteds. H1 is the opposite of that. There is a preference. There is a difference. But again, if you want, I'm going to allow you to shortcut this as or H naught O sub I, my observed values, equal my expected values. Where O sub 1 would be cherry. E sub 1 would be, so O sub 1 would be 32. E sub 1 would be 20. Does that sort of make sense? O sub 2 would be the observed strawberries. E sub 2 would be the expected strawberries. O sub 3 would be the the observed oranges, and E sub 3 would be the expected oranges. And then H1 would be O sub I is not equal to E sub I. Okay, so you all are doing this one with me, correct?
Yes.
Perfect. Step 2, what's my alpha? Or what, yeah, what's my alpha?
0.05.
Perfect, 0.05. Next, we're going to compute the test value, chi-squared, and p-value using the goodness of fit test. So if you have a, does anybody have a TI-83 calculator?
Yeah.
Okay, so I didn't bring my tools. I need to bring my tools next class. So for today, hop over, if you're using a TI-83, hop over and use the calculator on the computer calculator for a minute. You can use the one next door then if you want. And you need to change it to an 84. So everyone open up Wabbit Emu. Shauna, use the computer next to you. That's all you do. And does everyone have access to it? And do File, Open, and then, shoot, really? There isn't an option here for,
Why on the top? Oh, that's funny.
ROM. Go down to ROM, see if it gives you any. No? Library? Did you, are you folks finding this? It should be in here.
Yeah. Is it, there's a bunch of different like TI-84.
Okay, so it should be easier for you folks to find it. I don't know why I can't find it.
TI-84 plus or TI-84.
Yeah, you want 84. You want one of the 84s. If you file open, it should open you up to a spot where they're already in there,
Got the silver edition.
and you want to pick an 84. One of the 84 options.
Okay.
I'm going to pause this so we can make sure everyone's on board.
Did you put it?